crap, I didn't present. Yeah, screwed up. Okay. Can we all see the lecture slides? Okay, so let's get started. Last day we had talked about sort of the sensory processes that are involved in the performance of motor skills. And then we had finished off with talking about vision as sort of preferential for us when we're learning motor skills and when we sort of complete different motor skills. And I don't know if you guys had a chance to sort of look at the Cristiano Ronaldo video, but that was a example of using blinding the vision. And so what they would do is they would have someone kicking the ball to Ronaldo, and in this case, and then they would turn off the lights and see at what time frame it would most impact his ability to like sort of return the soccer ball and kick it into the net. And with the professional, so Cristiano Ronaldo, he was able to do it with turning off the vision, like making everything dark, even before the ball was released into play for him. Whereas when they compared that to the amateur, when the lights were off, he was unable to sort of perform that task. So it just goes to show that as we get better and better and better at performing a particular type of motor skill, we get better at using vision more efficiently and being able to pick out what's the most important, and then also being able to understand our proprioception better. So we're better able to utilize the senses that we have available with practice. Does that make sense, everyone? Okay, perfect. And so with today's lecture, we're going to be talking about vision, and we're going to be talking about central versus peripheral vision again. And last day, we had finished off with talking about how there's two streams of vision. There's central vision, which is the first, like the 2 to 5 degrees of vision is what we focus in on. That's allowing us to really pick out the important features of the environment. So it gives us distance, estimate object weight, picks out sort of all of the regulatory sort of conditions that would modify our movement. And then peripheral vision is in the periphery, and that picks up motion. So that's what we're sort of not aware of, but we can notice the peripheral vision, and that's for picking up motion. Okay. Everyone good? Now, I want to just, before I get into the new lecture slides, I do want to talk about the sort of lab. I've had several students sort of email me in regards to potentially having a TA just set up a quick session on how to do the labs. I know, like, I want to thank you all for sort of bearing with us as they try to figure out what to do. And I think that that's what we should do. I think that we should set up like a Zoom call with one of the TAs, and that he could or she could go over sort of what's involved in sort of implementing and completing it and then submitting it. And then anyone who is sort of has questions in that would have them all answered right there. Is that good, everyone? So we'll see. Like, there's no. Has anyone had any problems with submitting the current lab report? Should be fairly easy. Oh, can I ask you guys a question? Is next week reading week?
Yeah.
Yeah. Okay. Oh wait, hold up. I gotta turn up my. Okay, perfect. Okay, awesome. Well, boom. Week off. I still work, but I know you guys are gonna miss me. It's gonna be just like super difficult, but just know that if you need me, I'll be there. Would it be possible to have the lab due at sure. Laura wants to do at 11:59 because she got thing on the go. Okay, so let's get started. So the topics of today's lecture are motor performance and talking about action preparation. So motor performance, we're going to talk about like different types of skills. And now that we sort of talked about sensory processes and how they're important and how they've been studied in different studies, now we can talk about how studies have looked at individual types of motor skills and looked at how sensory processes are utilized in each of those specifically. And then the second half of the lecture is going to be talking about action preparation. And action preparation is what happens in the cognitive processing time, in that reaction time. Obviously, there's things that the brain is putting together. So let's talk about what that could potentially be in research that has looked at that. So the breakdown of today's lecture is we're going to first discuss different types of skills, and then we'll finish off with action preparation. So like I said, we talked about sensory processes in the previous lecture. And then today we're going to be looking at, and does anyone have the textbook? Because if you look at the textbook, they sort of cite all of and talk about all of the studies that we're talking about in this lecture. But research has been essential in sort of advancing our understanding of motor control and processes, and it provides, like, so let's, if we study a type of motor skill, gives us an idea of what's involved in putting together the motor skill, like what the things that you need to be about, what about sensory processes is necessary for that motor skill? Is it vision? Is it perception? Is it what have you? Now, if we understand how we control our body in a particular type of motor skill, that gives guidelines to practitioners in like a clinical environment on how we or what we should consider when trying to rehab them. And so hopefully I give you some examples today that will give you an idea of sort of what's entailed in that. So the first thing that we had discussed previously is one thing that was sort of evaluated is that with like reaching tasks and pointing tasks and tasks in general, we've quickly realized that there was like sort of a speed accuracy trade-off. So the faster you did something, it led to more errors. And if you wanted to do something very accurately, people tended to slow down their movement. That's something that we've seen in all types of different motor skills. And so that was called the speed accuracy trade-off. And so initial studies wanted to look at, what is some of the rationale behind that? Is there any sort of like rules that is imperative to understand when does this apply to all motor skill? Does this apply to only discrete motor skills, for example? And so researchers wanted to look at first that because it was something that was commonly known. So this study in 1954, so this was a long time ago, it was done by Paul Fitts, and he developed what was called Fitts' law. And this is the setup for the experiment that he designed. And so what he did was he had a subject, you guys can see on the screen. He had a subject that would take a stylus or a pen and rapidly tap back and forth these targets. And what he did was he measured the distance. So he varied the distance between the targets, and he also varied the target size. Okay, and then the object of what the subject had to do was tap in between the targets. What he did was he altered the distance between the targets and the target size and looked at how that would affect movement time. And what he did was he plotted all of that for various distances and target sizes, and he developed this sort of equation. He found that there was like sort of like a logarithmic sort of graph that he could make and to estimate what the movement time would be. And so he developed sort of like what was called an index of difficulty. This is what the equation was that he determined. It was just like sort of an exponential equation that he took from the graph that he designed or developed in his study. But it was the first time that they put like applied math quantitatively to motor control research. So this is the first go. This is 1954, right? But he developed what was called, so if you took the exponential, so this part of the equation, that dictates the slope of the curve. And so that part is what changes with difficulty in terms of target size or distance. And so they called that the index of difficulty, that part of the equation there. And so that would mean that a higher index, so the index of difficulty, the higher the difficulty, the slower that the person would move. And it wasn't like a fully linear equation or line. It was exponential. So that's why there was log in there. So this was the setup here. So the index of difficulty for his study was the log base 2 of 2 times the distance between the targets divided by the width of each target. So the smaller the distance in between the smaller the target, so the smaller the width of the target, or the larger the distance between the targets would increase the movement time, which makes sense. So here's an example of index of difficulty, right? Because it's the width between so in his study, it was the width between, or sorry, the distance between the targets and then the width of the targets. So here we have an example of 2 different examples of the targets that would be index of difficulty 3. So you would have either 1 centimeter targets that are 4 centimeters apart, or 2 centimeter targets that are 8 centimeters apart. Those would both equal an index of difficulty, according to his equation, of 3. Whereas if you took something that was like this, so these both of these examples are the same distance between targets, 2 centimeters and 2 centimeters. However, these targets are 2 centimeters in width, whereas these are 1 centimeter in width. So this would be an index of difficulty of 1, according to his equation, and this would be an index of difficulty of 2. Now, the point of this study was that they were able to quantitatively apply sort of like an equation to motor control. So there was the first time that they had developed, in this case, a law applied to how we control our bodies. And it was applied to one thing that they had noticed in lots of different fields, that the faster you will do something, it's associated with decreased accuracy and vice versa. So that's why it was an easy thing to start off with. Now, Fitt's law has, as that was in the 50s, right? So that was continued on, and sort of that index of difficulty idea, right? The speed accuracy trade-off, it's been shown in lots of different tasks since then. And you can look in the textbook at different examples, but things like dart throwing, moving a computer on a computer screen. One that's important for us as like sort of rehab therapists is this whole pegboard manipulation task. So with stroke patients, how they have to retrain the motor skill of reaching and picking something up. They use this pegboard task here. And so they say like move yellow to another spot, right? And so they're practicing looking in an area, reaching and grabbing it and moving it. And so the speed accuracy trade-off has applied to those. And then on this sort of picture right here, they have shown that the speed accuracy trade-off is also sort of held true with reaching and grasping type tasks, where you have to reach a tool, open something, lift a container, all those kind of things. Some of the principles of Fitt's, a lot of these are older sort of like technology examples, but they can be applied to sort of technology. And here's an example of how motor control research led to sort of ideas on how we consider how people move in the development of daily life stuff. So according to Fitt's law and the speed accuracy trade-off, more frequent tasks should be positioned closer to the average position because it's less difficult, right? And tasks done more frequently should be assigned larger buttons. That's just based off of this whole idea of index of difficulty. And that's what you see in sort of like consoles in cars, sort of all of the apps and buttons on cell phones. Same sort of idea. Any questions? Awesome. So this is an application of something that they learned in motor control research, right? So it's a kind of sort of an easy example. And now let's look into what they continued on in trying to understand the specifics or other types of things that are factors in controlling our bodies as we're performing different types of tasks. So a reaching and grasping task would be sorry, a manual aiming task. So the pointing, that would be called a manual aiming task. So that's where you reach and you touch something, right? So something like putting a key in a keyhole, for example, striking a key on the keyboard. It's reaching and pointing. Okay, that's called manual aiming, just like in this study. And what other studies wanted to do is that like understand what control aspects are happening in the performance of that task. And so what they sort of wanted to understand was A, how the control of the body occurs during the performance of that skill. So in the beginning, there's an open loop control. So let's say I want to reach and point at something. I look at where my target of where I want to point at, and then I develop, think about the motor program-based theory. So I take the specifics of what I want to do, like the environment, right? How far it is, distance, direction, and then I put that onto the old motor program for that motor skill, and then it's sent out. If things are done in an open loop system, does that mean that there's feedback or there isn't feedback? No feedback. That's correct, Apollo. And so if there's no feedback, what are one of the factors that mean that we would move in only an open loop situation or an open loop circumstance? What was one of the biggest factors to dictate if we can use feedback or not? Speed, yeah. So it's whether or not there's time. So initially, when we perform a motor skill, reaching and pointing, it starts off as an open loop system. And then if there's enough time when we get to close to movement termination, so let's say we're talking about the keyhole example, then we will have an opportunity to correct our errors based on feedback from vision, from touch, from proprioception, perhaps. And so in this case, with reaching and pointing, when discussing how we control our body, we initially start in an open loop system. And if there's enough time, we can now start using feedback to make that accurate. If we wanted to make it more accurate, we would slow down to make enough time so that way we can use feedback and then operate in a closed loop control situation. So this slide just dictates that we start off at a move initiation in an open loop system. And if there's enough time at movement termination, we will start to use feedback to make our, to refine our movement to make it more accurate. And then that would be feedback, so closed loop. Right. One more time. Okay, boom. So studies wanted to look at, okay, if vision is preferential, what does vision specifically do in this type of example? Like, do we look at something and then we don't need vision? Do we look at something, evaluate what needs to be done, and then we can look around and then look at it at the end? Or do we have to, like, think about it. When you put in a key in a keyhole, do you look at it the whole time? You tell me. Do you need to? There's always the horror movies where they're like screwing around and like, right? Trying to go fast, so they maybe don't have time for feedback, and then they drop the key, and then they get like attacked by the monster. Research looked at how vision's used in like a simple reaching and pointing, right, or manual aiming task. So here we have an example of putting a key into a keyhole, and it looked at how vision, or they determined that vision used differently in the preparation phase, the initial flight phase, and the termination phase. And so what it looked at when evaluating people doing this is they found that when someone's going to start the reaching and pointing task, they look at the area. That makes sense. So let's say I'm put key in a keyhole, or the targets for the Fitts law experiment, or striking a key on a keyboard. I look at where the location is and kind of look at the regulatory conditions that are going to help determine what I need to do to accomplish that motor skill for that situation. So it's going to dictate sort of the distance, the location, what are the factors, if there's any hurdles in the way to complete that task. In the initial flight phase, what they found was, so someone will look at it and then movement will start. So once movement starts, what they find is that that is when it's operating in an open loop system, the movement happens. What they see is that in that phase, you can stop looking, but your peripheral vision is always going to monitor to make sure that your hand is moving in the right direction. So right now, so you like, look what you got to do, go to point to it, and then you can maybe look around as peripheral vision, because it can take peripheral vision can see so much more. It will monitor movement. And so that's what they determined. And then they found when doing all of these reaching and pointing tasks, they found that at 50% of movement distance is when the person will start to and look back at the target. And the one thing that we finished off with last day is how we time our movements is in this whole concept of TOW, or time to contact. We look at the object and the relative sort of change in the image, or the size of the image, and we use that in timing our movements. So what we're going to see is that there's always sort of a look at the specific object to dictate when we time our movements. And we're going to see that in this motor skill, but also all the other ones moving forward. So that's why time to contact was introduced in the last lecture, because it's sort of how we time our movements. And so this is not the last or seventh time we're going to hear this. This is going to continue to be something that we talk about throughout the course. And then in the last phase, what they found was that so that we look at the key that's going to tell us time to contact. Once we make contact with the target, we tend to focus our vision on that, so that way we can make sure that the sort of target was reached, just to confirm. And then we can also use proprioception, right, in that circumstance. So that was how vision was used in each of the three phases. The names of the phases aren't typically like important because they change with each task, but it's getting an idea of how we use vision. We have to use central vision to look at the regulatory features, right, initially, to dictate what we need to do. Then during movement, peripheral vision monitors movement, and then our gaze turns to the target at 50% of the movement time, so that way we can time our movement, or we can judge when we're going to touch the target. And then once we've reached the target, we use vision to make sure that we've touched or reached the goal. So that was reaching and pointing, or manual aiming tasks. The next task that they looked at was prehension. Does anyone know what prehension means as a term? It's like, so prehensile thumb, like monkeys have prehensile thumbs, we have thumbs. Prehensile tail is it's movable. So it can be used to reach and grasp for things. For the motor skill of prehension, it means when we grab for something and grab it. Now, the reason why prehension tasks, so reaching and grasping for something to manipulate it, is different than reaching and pointing, is because depending on the target, think about lifting, think about when you pick up a hammer versus when you go to pick up a cup, versus when when you go to pick up a cup. See how my hand changes each time? The reason why prehension, or reaching and grasping, is a different motor skill than just reaching and pointing is because depending on the object we're going to be like grasping, it changes our hand positions subconsciously. So I look at the cup, this is what I want to do. I look, like, go to pick up like your phone. Your hand is already positioned on how you're going to manipulate it when you're going to pick it up. Like when you're gonna, like the end way you're gonna use it is considered in how we grasp. And that happens in like a split second. And so that's why they're two different motor skills. And then research looked at, again, those three different phases to see if maybe there were some rules that they can give us, or they could develop in understanding how we control that, that motor skill. The first thing that they noticed was, depending on the object that you want to grasp, your hand profile changes immediately. So clearly in that initial, like, sort of like action preparation, your body is considered, subconsciously considered, what the final sort of end position is, and it's put that into the motor skill. So the three areas where they'll want to look at what vision is going to do is they wanted to look at transport, the grasp, and then the object manipulation phase. Because initially we go to reach for it, then we grab it and take hold of it, and then there's the intended use of that object. Selena, does this have anything to do with when you go to grab something with the intention of knowing how much force? A little bit, yeah. No, it's kind of the same thing. That's called the size weight illusion. But it's a little bit different, but it also relates to the fact to this point that when we have an intention of what we want to do and then look at the object, our brain, like those motor planning areas, have put together all of that into how we perform the motor skill. So that's kind of the rule, Selena, and for everyone that's listening. Which it's interesting, right? So within a complete, so because I've already learned how to pick up a cup, I'm familiar with doing it, right? Like I've in a split second, my body has decided, like, look, like you try to grab for a cup, your hand is already like this. It's ingrained. Weird, right? So then, like, imagine picking up any one of these things. Like, imagine you're gonna go pick up, like, so I don't know. See, this is where in real life, I would have had like people go to pick up something. So go to pick up a mug, go to pick up a hammer. Like imagine going to pick up anything on the screen right now and look at your hand. It's already altered based on the object that you're going for. Because we've learned a motor skill. Each one is an individual motor skill for that type of object. And so this is important for like stroke rehab, that you don't just use a pegboard. Before they used to use a pegboard, right? You move from one here to one here. You practice gripping, moving it. But each time it's a different type of skill or different type of object. It's a new motor program. So that's why with stroke rehab now, it's like brushing your teeth, getting changed, doing buttons, picking up a cup, cutting food. Each one is an individual thing they have to relearn. And you can't separate it. You can't separate the two. You can't practice pointing. You can't practice gripping. It's one skill. What age does your immediately with experience? So usually as like people are like 3, they start being able to grab stuff. As soon as they start being able to grab stuff, yeah. Could you imagine, Megan? Up to kindergarten, kids can't like do anything. They're just like, and then you have to like feed them. Rayuda is asking, how long does it take for sensory information to get used to an object? It's all repetition. So that's motor learning. How long does it take you to do a new skill? Well, if it's something similar to something you've already learned, less. If it's something you're completely unaware of, a lot. What if you don't have all sensory processes? That's going to take you more. Yeah. So this is saying that this is proved, and this is why it changed rehab in the sense that you can't propose independence of the two, reaching and grasping. It's got to be the same. Okay. And so some of the things that they saw in research was that it showed a strong, temporal coupling. So there was a coupling of the timing of the movements. And so what they found was that when people were reaching and grasping for an object, and they would monitor them, right? They would say that the size of the object, so depending on how big it was, changed when they would have their maximum grip aperture. So watch when I'm reaching for my cup, I'm immediately opening my hand up as far as I can go so I can reach, because it's a big cup, right? Extra large. But okay, so what if I'm picking up something small, right? Like I go for it and then it takes longer for me to reach the maximum aperture. It's just that's something they noticed, which is weird. They noticed that grip closure. So we open our hands and then it starts to close at 2/3 of movement time. So what they thought was, remember how at 50% time of movement time, people tended to look at the object. So maybe that's what it is. You look at the object, you're still moving, and then you start to like reach for the target and grip and manipulate it. Okay. And then so what if someone goes to reach? So this is what they noticed: if someone had a cup, right? So I would go to reach for it, and they moved it halfway. The person stops and resets. So it's not like the hand stays and then just so let's say I'm reaching this way, it stops and then is moved. That whole movement stops again. See, like I go reach for it, it's moved. So I'm like, oh, so then I reset the movement because it's ingrained. That one type of movement is how it's memorized in our brain. It's one linked. It's linked. It's not just moving and then gripping. Does everyone get that? That's weird, right? I mean, it's all stuff that would like you probably like never really considered. It's obvious, but then like only if you like really pay attention to it, which we really don't. So when talking about how vision would be utilized in this particular test, let's talk about certain ways, right? And so what they found was that in the initiation of movement, vision would be important to look at the object, determine like what object it is, and that's going to help us determine, you know, the distance to the object and the type of like grip you wanted to like sort of manipulate your hand. So that's going to be ingrained. During transportation of the hand to the object, this whole idea of time to contact is going to be important. So at like 50% movement time, we're going to look at the object and it's going to tell us the timing of when we're going to be reaching the object. And then peripheral vision in movement is always, sorry, peripheral vision with a motor skill is always monitoring like sort of movement, background movement. And then when we grasp the object, people typically tend to look at it. So that way we can supplement the tactile feedback from touching and proprioceptive feedback. So that we're aware of, okay, so its grip is tight, this seems stable. We can also look at it. Yeah. And then so clinically, this affected the ways that we were able to sort of modify rehab. So you make sure that reaching and grasping is the motor skill for different types of objects. So this is handwriting. This was the next skill they looked at. Now, I don't know if someone wants to share their screen and we can like take volunteers, but typically what I would have to do is I would ask the question is we talked about motor equivalence, how depending on, it doesn't matter if you use your mouth or your hands or your feet to write your name or like a word, our sort of like cursive writing style is ingrained in our brain. And then whatever limbs are available is how we sort of implement that. That shows motor equivalence. So that part of course, it's a cognitive skill. Like we have to determine what we want to like say, but the motor skill of the action of how we write it is a motor skill, and that's ingrained in us. So what research wanted to do was sort of look at how is vision involved in handwriting. So let's write. Okay. So does anyone want to share their screen? Or you guys just want to do it? Does someone share their screen? I think I pinned it. So what I want someone to do is, how do I make it so I'm not, does anyone know how it would make someone else come on the screen? Oh, but I'm presenting. Is that the deal? I have to unpresent and then someone's got to come on? Any day. Yeah, why not? Sure, let's do it. Okay, ready? Good. Now, what I want you guys to do, someone share the screen. We got a volunteer? Who wants to start presenting or present their screen, or how does that work? Drew, look at him. There he is. Oh, sun's out, guns out. Look at him. Look at him. Okay, so what I want you to do is you're going to like move your camera down, okay? And then you take a piece of paper and I want you to write 5 times, I like to sit and read books. Okay? And what you're gonna do is you're gonna look at us while you're doing it. Okay, so you're gonna write it 5 times, but look at us. So then we're gonna see how screwed up the writing is, because that's gonna tell us what vision does when we're writing. Is that weird or you're good? Okay. I like to sit and read books. Courtney says she did hers just now, and it looks the same. Wow. Cheers to Courtney. Look at her. Wow. Oh my God. Wow. You must. Well, the one's kind of over. Is that? I don't know. Maybe you're superhuman. Maybe you should teach this course. Is you done? You're not done? Yo, Drew doesn't even know how to write. It's okay. He's actually typing it out. Okay, let's see. Hold it up. Hold it up. Hold it up. Hold it up. Okay, so what are some of the things? There's any spelling mistakes? There you go. Okay. Can everyone see? Well, you guys will see in the video. So then, did everyone see that? Can everyone see that? Did that work? The way, because I'm gonna do this again, okay? So now I'm going to go back and present my thing. And I screwed up. Can you guys see my stuff again? Yeah? Okay, perfect. Okay. So, no, we couldn't hear your mic. You were muted. But buddy, my writing is worse, so no judgment here. But what did we notice is that the writing, like, so even with you, Courtney, a little bit, like the writing was off. So vision is going to be like important to make sure that we write on the line. So here's an example of what we see. Also, we saw that there was also like spelling mistakes. So this is an example of the study when they did it. There was spelling mistakes. Things were out of order. Words were like written on top of each other. And so vision is used for feedback in a closed loop system to sort of, when we're writing, we just look at it to confirm sort of the words that we're implementing. Does that make sense, everyone? Okay, so now let's talk about bimanual coordination skills. Does everyone remember what that means? Bimanual coordination is when you do a motor skill that involves the use of both hands at once. So symmetric bimanual coordination is when we do a motor skill that both hands are doing the same thing at the same time, like rowing a boat or pushing a wheelchair, right? Asymmetric bimanual coordination is when we have two hands doing a skill, but both hands are doing something different, like playing a guitar, playing a piano, serving in tennis, lots of different things. So what they wanted to do was sort of evaluate. So what are some of the things that we notice when people are doing bimanual skills, asymmetric bimanual skills? So I'm going to stop presenting again. What I'm going to have someone do is with one hand, I want them to, so with the left hand, draw a circle, and then with the right hand, draw a triangle, and then do it at the same time and see what the difference is. So then I got to do this. Okay, now I'm going to unpresent. Now, who wants to present their screen and then do that for us? Drew already went. Courtney talked a huge amount of games, so I feel like she maybe really wants to do it. Do you want to do it? You don't? I can't hear you.
I kind of do, but it doesn't look good.
Yeah, so yeah, it's not supposed to look good. You guys are supposed to make me look good. So wait, do you want to do it or do you want someone else to do this? Who else is, there's three people sharing their screens. Do you want to do it, Courtney, or do you want to do it, Rayuda? Rock, paper, scissors. You want to do it? Here, Rayuda's going to do it.
Okay, so I'll do it. Yeah.
Yeah. Okay, so what you got to do is with your left hand, take a piece of paper, left hand, you're going to draw a circle. Right hand, you're going to draw a triangle, then move down, and then do the same, like do both at once. But show us what you're doing. Got this. Yeah. Well, yeah. There you go. Okay. Let's see what you got. Okay. So no,
I tried.
yeah, whatever. Like I'm not better. So it is what it is. You know what I mean? Motor control. Okay. Let me just do this. I'm gonna start presenting again. Okay. So what they noticed, can you guys see me? Kind of. Yeah, we're all good. Messages. Good. Okay. So what they noticed was that when doing it, the hand that does the less difficult task will slow down for the hand doing the more difficult task. And then they will see that initially and you saw this with Reuta, is that initially the arm movements, so both the circle and the triangle, resemble the triangle because your brain is trying to concentrate on the more difficult side. And so it implements that on the less difficult side. It's just the way that it is. And so what they found, and you can like, if anyone teaches sports, what they found is that it's a lot easier to teach one, then the other, and then add them together than to just start with doing them both at the same time. Now, obviously, it's a little bit more difficult. Like we're talking about skills that are a lot more difficult than circle triangle drawing, but the things like playing a guitar, you learn how to strum and you learn how to fret and you put the two together and practice. And so what researchers wanted to look at was with specifically asymmetric bimanual skills, what is the role of proprioception and vision feedback, right? So for skills that are doing two hands at once, sometimes you can't look at both hands at once. So it's better to look, practice, and then add the two together. Does that make sense? Cool. Okay, so the next skill we're going to look at is catching a moving object. Now, in a lot of respects, what they figured out was that catching a moving object is like reaching and grasping for something, like a prehension task, except the object is coming towards you. So you have to move your hand into like a position. You got to shape your hand based on where you think or what the object's going to be, and then time your catches. Okay. And so what they found was that vision is obviously a huge role in that because you need to see what you're catching, and you have to time where the ball is going to be, or the object, and then you have to be able to time sort of that grasping action. And so what they found initially was that, remember this whole idea of tau? So they wanted to, remember this is old research, right? Do they say, okay, so do you look at the object where, like, so imagine catching a ball. Do you look at the ball, figure out where it's going to be, and then wait for it to hit your hand and then grasp? No, what they found was that people would look at the object and start their hand closure even before the ball's in their hand. So we've assimilated, or we're estimating, time to contact. And again, there's the example of tau. We have to look at the object and the relative size of how it's changing. We're able to sort of time our motion based on that. And so what they found was that when they analyzed, like, good catchers versus bad catchers, they found that a lot of the errors in when they're unable to catch is based on grasping errors. So they're unable to time them. It's on like, so they're able to see the movement initially, right? Because when you initially see the ball, you're able to get a better idea of where it's going to be. It's the vision at the end where they want to time their hand closing motion. That's where the most error in catching occurs. So then they wanted to see, or they wanted to look at, well, so imagine someone catching a ball, and I'll ask this question after the class. So do you look at the ball the whole time? Do you need to? When is vision necessary when catching a moving object? Right. So Apollo says when predicting the path, and that occurs when we think of the Ronaldo video from last day. We are able to estimate where the ball is going to be located based on the initial flight path. So when someone's going to throw a ball, we look at it for a split second and estimate where it's going to be. And then when it's mid-flight, you can look at other things. And then it's necessary to look at the ball again just prior to hand contact to time our hand closure for time to contact. So vision is necessary when catching a moving object, initially to estimate the location of where it's going to go, and then prior to hand contact for tau, or time to contact, to determine when to grip our hands, or like to start hand closure. Cool. Now, I had kind of touched on this a little bit before. I'll play the video as I'm talking. But a lot of different motor control stuff has come from where they like model. They take machines and they make it similar to like the specifics of humans, like all those like Boston Dynamics stuff. I don't know if you guys have seen that, but it sort of, by putting all the machinery together and seeing how it runs, gives us a better idea of how we run. So with this whole idea of like the drone, where it's not one central computer that controls everything, it's like 4 mini areas that sort of control its to make it level, and then as a central sort of like executive that sort of monitors everything. That's how we work. There's the central executive, and then there's so much that happens from reflexes. This is an example of like a catching machine.
Roland Justin performs dynamic and sensitive tasks. Catching a thrown ball with the hand is not easy. A tight interplay of fast perception, a good catching strategy, body control, and dexterity is needed. Stereo cameras track the balls, and an IMU measures the 6D head pose to account for not completely cancelable vibrations introduced to the robot's lightweight structure due to the rapid catch motions. Based on the continuously improving trajectory predictions, a real-time path planner running on an external cluster repeatedly decides where, when, and in which configuration to kinematically optimal catch the ball. The resulting joint paths are executed by the arms, torso, and mobile platform. The head joints are controlled to keep the balls in the camera's field of view. The hand closes at the planned catch time. For easy user interaction, an iPad-based interface is provided. The system robustly reaches the necessary precision of 2 centimeters in space and 5 milliseconds in time, leading to a catch rate of over 80%. Despite the challenges of vibrations, elasticities, distributed sensor, actuator, and computing resources, this is achieved by combining the right sensors, intelligently taking the different precisions of the kinematic subchains into account, and thoroughly handling all timings in the sub-millisecond range in the software.
So, I don't know if you guys found that crazy. Watch the video after, but what they do is they use this robot and they try to program it based on principles of what they found in human motor control research, and they're able to make it figure out how to do like these different tasks. So like catching a ball, like I don't know if you can see on the bottom, it does a whole bunch of different things. So this is like the Japanese version of Boston Dynamics. I don't know if that's fair to say, but this is also a lot older. Cool. Now, one thing that research also wanted to look at is obviously vision of the ball, like the object you're catching, is necessary initially, and then at the end to time you're reaching and grasping, or the grasping of the object. Now, is vision of the hand, of your hand, also necessary when capturing capturing it? And so what they did was they so let's say someone's throwing a ball, right? So what they did was they made their hand visible and not visible in this particular study. Now, what do we know about peripheral vision? What does it do? It monitors what? In movement. So what they found was that when people don't have vision of their hands, they have positioning errors. So they found that when people were unable to see their hand, right, because you're looking at the object, but you can still see peripheral vision telling you where your hand is, that without vision of their hand, they were unable, they had more errors in like the final positioning, like their hand was in the wrong spot. Whereas with vision of the hand, typically your errors when catching an object is more about grasping, or like more about like a grasping error. Now, what they found was that the more experienced you are, the vision of the hand isn't as necessary, which makes sense. You're more aware, or you're better. Remember, one of the key themes in this course is that as you become better and better at performing a motor skill, you less require vision and you're better able using your own proprioception. So this was this study here where they looked at like people that were experienced and non-experienced catching an object. And so people that were experienced, 19 times out of 20 were able to catch the object, whereas non-experienced people were like 16 out of 20 or 15 out of 20. When they had no vision of the hand, it was less accurate, but still pretty good. And what they did was they looked at what the actual errors were within the grasping or position, like the final position of the hand. And so what they found was that inexperienced people had much larger increase in positioning errors versus the experienced people, which just proves that experienced people are better aware of where their hand is without vision, therefore proprioception. Okay. Next one is striking a moving object. So striking and moving objects is similar to catching a moving object because it involves intercepting the object. So instead of catching it this time, you're trying to hit it, right? So you're manipulating something else to sort of accommodate or perform that motor skill. Now, this is similar to catching a moving object, but a lot of the research looked at baseball players. Are there any baseball players in the class? Really? No one plays baseball? Is there one that plays virtual? What is it, like gaming? Is there a gaming baseball league? Okay, so anyone that plays baseball, or if you just want to answer, if someone throws a fastball versus a slower pitch, what changes? Is the swing slow down, or does the timing of when you start the swing change? All right, Brandon. Timing. Everyone says timing. That is right. Right? But that was something they had to study. Now, the other thing that they noticed is that what's the difference between like amateurs and pros? And what they found was that the difference between someone that's pro at like hitting a baseball versus someone that's like a semi-pro or an amateur is that the head movement is so much less with people that are pros. So as they get better, they're able to make sure that their head isn't moving. Now, why would that be? Is because if their head is stable, they're better at using their vision for time to contact. So if you look at this example here of like, these are like, it's gonna be probably lame, but they're people playing they're baseball players swinging a baseball bat. Look at their head. Their head doesn't move. It's like focused. The music is dumb. But look, okay, see how like look how much the body is moving, and then look at their head. Their head is their vision is like locked in. So with a stable head, they're better able to keep their eyes on the object, which allows them to improve their timing because it's the timing that changes of when they initiate their swing. Their swing is the same regardless of the type of pitch. It's about whether or not they're able to time it correctly. Do you feel that's true, Brandon? Yeah? Brandon? Anyone? There you go. So by having a more stable head, they're able to make sure that their eyes are picking up the location and the speed of the pitch for proper positioning as well as time to contact. Any questions about that, guys? Any comments? What else is left? I think that's almost it. We have one more left. Locomotion. So just walking, right? So the one thing with walking that is important, because walking is a continuous skill. So it's a little bit different. Walking, you get started, and then your central pattern generator helps the rhythm of walking, and then we continue on, right? So they wanted to look at the different sort of aspects of sensory processes that are involved with walking. So this one is important because we have central pattern generators that sort of maintain the rhythm of walking. And then based on dynamical systems theory, it's suggesting that with the use of like muscle spindles and GTOs, that when we speed up the rhythm of walking, the pattern of how our legs move sort of all just sort of like occurs. So therefore, what are some of the things that we want to investigate in motor control in relation to locomotion that's a little bit different than other motor skills? So one thing that they notice is that walking and locomotion and running, they have a rhythm base to it. So with these like sort of rhythm, sort of continuous motions, so much is based on rhythm. And so they found that with the rhythm, they could teach that to sort of like rehab patients to help them improve the rhythm of, so relearn the rhythm of walking. Because that way, when we walk, we don't concentrate on what we're doing, right? We don't like left foot, right foot, left foot. It kind of just happens. So what they found was that with rehab patients, like stroke people that are trying to walk, if you help them like sort of get them moving their arms and their legs in a rhythm, it helps them not have to focus on that. And then they can concentrate on what people really concentrate on as they're walking, which is the path that we're going to learn is the path and the like distance, picking up motion, that kind of stuff. Here's an example of a research study that was just evaluating walking. I don't think it's that important. Any questions, guys? Because other things that they found in research was that people that had sort of like CP patients or patients that had sort of pathological conditions, they found that their gait would be like they would choose an inefficient gait to make sure that their head was stable. So just like the baseball players, they would find that in terms of like what's priority, your body would accommodate a inefficient sort of like gait cycle to make sure that the head was stable. So with CP patients, they almost walk in a way that sometimes isn't the best that they could do like, in terms of like efficiency, but they do it because their head has to be stable so that they can use vision. Just like like we're always saying, vision is preferential, right? And the other thing that they found that was interesting is that the transition from walking to running, they couldn't come up with like there's always for everyone there's a speed where they choose to run versus walk, but that they can't predict it. It's based on the person. So that was sort of weird. So then they ask, okay, so we have central pattern generators to make sure that we can focus more on the path. We saw pathological conditions that prove that it's important to keep our head stable. So what are we looking at when we're walking? And they looked at studies of maybe we can evaluate what people are specifically concentrating on when we are walking. So typically people will look at sort of the path, and then they will use their central vision to determine whether or not they're going to contact objects. So let's say you had to, for like high jump. If you had to high jump, you are aiming for a target. So just like we're looking at the path, if we have to make contact with a particular object, so let's say it is like a specific spot where you're jumping in high jump, or you may have to make contact with the ball, we would look at the object to time our walking or our running to make sure we made impact with that. So here we have another example of time to contact. The other thing that vision is important for is when we look at the path, it's also going to let us know if there's objects that we have to avoid. Right? And do you remember when we talked about dynamical systems theory that came up with this whole idea of affordances? So if I see a curb come out, or let's say a stick falls out of, and like let's say I'm running and then I notice that there's going to be a stick coming up. I'm able to judge whether or not it's big enough that I can jump it or I have to step over it. That's all sort of automatic. But this was a study where they looked at high jump. And so like I'm not crazy familiar with high jump, but I think it's typically the same sort of like path. But what they did was they had someone do multiple trials of doing the same high jump. So it's the same path. So does that mean that they do completely the same like steps? Like it's exactly the same? And what this showed, which is common sense, is that the path's a little bit different. So initially, their strides were the same. And then as they get to where they got to jump off the takeoff board, there was a sort of a variation in their stride length. Which just means that with this whole like time to contact thing is that when they would get close to the object, that's when there was the variances. So they would look at the target and then modify their movements to make sure they made contact with the takeoff board. So it sort of isolated the zeroing in phase, which would be what we know now as time to contact. And so what can you imagine is actually happening is that they're running and then the last like little bit, they look at the target, determine the time to contact, and then modify their movement to make sure that they hit the takeoff board and then perform the skill. Any questions about that, guys? So what I did in the first like bit of the lecture, so we're like two-thirds of the way done, is just looking at different types of motor skills and then talking about the sort of the specifics that were studied to understand how or like what's involved in us performing different types of motor skills. Any questions so far, guys? Okay, good. Makes sense? Yeah. Hopefully, one thing like in comparison to intro to movement neuroscience, I hope that you have a lot of moments of like, oh, that makes sense. That makes sense. Because it's I find with motor control, it's like researching things that we've already sort of realized. That's only going to help like sort of us progress more with like sort of I'm rehab, right? So progress more with rehab. Okay, so the last third of the lecture is going to be talking about action preparation. So action preparation is sort of considering what we are sort of processing in that reaction time before we initiate movement. When we're about to perform a motor skill, we got to prepare our action, right? We got to prepare the motor skill. And so what is the brain doing in that time? What is it preparing? And so what we would do is we would look at studies that would modify things and see how that affects the action preparation or affects the reaction time. And remember how we talked about it in the second lecture, that reaction time was one of the first and most popular outcome measures because it was easily timable. And so this is way before like MEG machines. They wanted to look at factors that would affect reaction time and therefore action preparation. Action preparation is what occurs between deciding you want to do a motor skill and the initiation of that movement, the reaction time. And so by changing different variables, they can see if reaction time is affected and therefore it makes things more difficult or less difficult. And then we can get get an idea of the different things. Let's say if something affects your reaction time, well, obviously that was being processed because it's affected us, right? So this is the way that they sort of evaluated sort of processing before we had all of those really high-tech machines. So the one thing that we realized very early on with reaction time is that action preparation or the preparing of our movements takes time. Even for the simplest movements, there is a delay between, okay, I want to do something and performing it. Just like that simulator with the driving where all you had to do was stop. There's a reaction time associated with it, correct? So I want to talk about what research has found will modify our reaction time, because then it gives us an idea of the sort of variables that affect our processing. And so there was 7 main things that they realized in research that would affect reaction time. Therefore, this is what's going on in processing. So we're going to go through each of them, and then we'll finish off the lecture. So task and situation characteristics that affect preparation. And that's important because it tells us that that is what's being processed. So the first one is number of response choices, predictability of the correct response choice, stimulus response compatibility, 4-period length regularity, movement complexity, movement accuracy, and then the last one was repetition of movement. So let's first talk about the number of response choices. So what do we notice in the video initially on the first lecture, where as you increase the number of choices, it increases reaction time. That's called Hicks' law. And so what Hicks' law states is that reaction time increases logarithmically as the number of stimulus response choices increases. Okay, so if you look at the reaction time, it increases as the number of options of a response increases, because then your brain has to process of the 7 choices, which one is this? And this is an example of, Hicks' law used in like martial arts for like self-defense for like police officers. So this is an application of Hicks' law, and he's saying that when people do
component here that's huge, and that is Hicks' law, another scientific measure. Hicks' law basically says, I'm going to do layperson stuff because I'm not a scientist, that theoretically the fastest response time a human being can have is if there's one stimulus and one response choice. That if I add more choices, I slow down response time. And if I add more stimuli, I slow down response time exponentially. Now look at your defensive tactics manual, look at the average self-defense book. Our system has 4,000 moves. And I'm going, so you have no clue what to do in a fight, right? And obviously there are exceptions. There are some genetic freaks out there. And I always tell people, don't mistake the trademark for the truth. Unless that person is your bodyguard, the fact that what their accomplishments demonstrate doesn't mean that that skill is transferable to every single student. Does that make sense? In our train the trainer classes, the first thing a prospective instructor writes down is, do not show your students what you can do, show your students what they can do. Cool? Because we all get into that. We learn our parlor tricks and we go, hey, and then people want to learn it and it's dangerous. You need to demystify the whole process. Questions? So the Hicks' law, it's great to have a scientific measure, but what's your demo? That's the theoretical, what's the empirical? Well, if I'm over here like this, Tony does, and we'll do this slowly because we don't have any gear on and I'm getting old. I'm talking to him, my hands are up, we all agree this is instinctive natural position. Actually, you can do this fast. We'll do, and we'll go through a series of moves. He comes in with a haymaker. Okay, do you all see? I flinch, I push away danger. I'm standing in front of him, haymaker. This one you'll have to slow down. He comes at me with a headbutt. I flinch, I push away danger. He comes at me with a left hook. I flinch, I push away danger. He comes at me to tackle me. I flinch, I push away danger.
So what he's saying in the video is that an application of Hicks' law is that the quickest reaction time, and in self-defense you want the quickest reaction time, is if there's only one response. So he's saying that regardless of like the type of like sort of move or that you're trying to counteract, you should always have the same initial response, because that means you're going to have the lowest reaction time. Rather, if someone's going to punch at you with a type of punch, the time to calculate, okay, well, kind of this type of punch, that means I do this type of move. It increases the amount of processing that's required. So just have the same initial move for everything and then figure it out. Increases your reaction time. Make sense? Everyone? Cool. Now, what they found was the next thing was the predictability of the correct response choice. Okay, so that sounds a little bit sort of confusing, but if you take, okay, so let's say you have one of 2 options that will occur, and you have to respond, like, so if it's red, you can hit button red. If it's blue, you're gonna hit button blue, right? And then you count the reaction time that's associated with that task. If the person gets a hint or a pre-cue as to what's going to be coming up, so if they get a hint, it decreases reaction time, because they can start processing the motor plan of like red button versus blue button even before the stimulus has sort of occurred. So getting a hint or a pre-cue will decrease the reaction time given the same motor skill where there wasn't given a hint. This one is interesting. They found that, so this was the example that I sort of came up with. It's taken from the textbook. But if you, this is talking about stimulus response compatibility. So has anyone ever tried to been drunk and tried to make crap dinner after shags? And you're like, who's used a new stove? And then you have to sit there and look at, okay, which burner is this one? You're trying to it's annoying, right? You have to process it. So what they're saying in this example is that if the stimulus is compatible spatially with the response, that it leads to a decreased reaction time. So imagine you are going to cook on this stove for the first time, and these are the controls. You look at it, okay, so I want to turn on this burner, it's probably this one, right? Now go to this one. Imagine doing it the first time. I want to turn on this burner. Which one of these? You're gonna have to read the legend and try to figure it out. It's gonna take more response time. It's gonna take, more reaction time. You're gonna have to process it longer because the stimulus and response are incompatible when compared to this. Now, what you're gonna do in lab is what's called the Stroop effect. And you're gonna give it an example, or it's gonna be giving you an example of stimulus response compatibility, where you're gonna have to read the word, but you're gonna have to look at the reaction time associated with reading the word or the color when the color of the word are the same. So let's say red and it's colored red, and look at the reaction time difference when the words are incongruent with the color of the word. It increases your reaction time. So this is what you're gonna do in lab, but it's another example of stimulus response compatibility and how it affects our reaction time, which is simply just saying that it's affecting the amount of processing that's required. So Hicks law, more choices, more processing. If we're given a hint, it decreases the amount of processing. If the stimulus and response are incompatible, it's going to increase the amount of processing that our brain has to do. So all of those are going to increase reaction time. Oops. 4-period length regularity. So if you have, if there's a delay between stimulus and response, if it's consistent, so think about when you have the beginning of a race. You know how they the starter pistol, they change the amount of time in between the ready and then the starter pistol. So let's say there's a reaction time associated when there's the warning and then the reaction time when the pistol goes off. If the 4-period, the time in between the warning and the stimulus is the same, subconsciously we can anticipate it because we know it's always 2 seconds. Let's say it's hypothetically 2 seconds in between. So let's say the warning and then the gunshot was always 2 seconds. The second you saw the warning, we would subconsciously know that in 2 seconds we're going to have to react. So then we would already we would already have started our processing. So it decreases the reaction time. The second last one they looked at was movement complexity. And so what they would do is they would have someone perform 2 different types of movements based on the stimulus that they're given. So they have to do a 3-part move versus a 6-part movement. And so they looked at the reaction time. And so with increased movement complexity, the actual reaction time is increased, meaning that there's more processing required, which makes sense, right? With increased movement complexity, there's an increased reaction time due to an increase required in the action preparation to develop the motor program. I'm not going too fast. Is it is this okay, everyone? All good? Okay. Movement accuracy. So remember how we talked about how the more accurate the movement that is required, our movement speed actually slows down, like according to Fitt's law. What they noticed in research is that the actual preparation is also increased. So as movement accuracy increases, the reaction time also increases, meaning that we're sort of processing more to constrict our movement to make sure that it's more accurate. Whoops. What are we doing here? Okay, so the next one was repetition of a movement. So think about like darts. Okay, think about darts. So it's 3 in succession. So the reaction time. So if with repetition of a movement, I don't know if you guys can. Like, I'm trying to think of an example. If anyone can think of an example of where they're doing the same thing multiple times. The first time there's a reaction to plucking. Sure. With every repetition, the reaction time decreases a little bit. Because if you're implementing the same motor program, there's less processing required. So the increasing the number of repetitions decreases the reaction time. Does that make sense for everyone? If you're doing the same skill like in quick succession, or hitting a button 5 times in a row, to look at the button and then go to press it, and then the reaction time would be less for the repetitions of the next series of repetitions. This one's hard to explain. I use a basketball example, but there's a psychological refractory period, or there's like a fake. So there's a time associated with, if you get, like, let's think about sports. If you deke someone, let's say, okay, so in basketball players, any basketball players? So let's say you're dribbling and you want to get by a defender. And so the best way to get by them is to kind of like fake them out. Pretend you're going to go one way and then go the other way. Does that make sense? You're trying to get around them. Even for hockey, for soccer, dribbling, like same thing. You're trying to fake them so that you can get out. One thing that they noticed in motor control research is that when you fake someone, it's like they anticipate that you're going to be going one way. So there's a reaction time associated with that movement for them to go block you. If you have successfully faked them and you get them going in one direction, they can't automatically stop and then go the other way, right? When you're faking someone out, you get them going one way and then you have an extra amount of time to go in the other direction. There's a psychological refractory period where they initially, like, if you fake them out and they go in one direction, they can't stop immediately. Their body has to sort of maintain the execution of that motor program a little bit, and then they can go the other way. And then they can respond to the way that you actually went. So that's called a fake. And this was the study that sort of proved it. So let's say this is the reaction time of someone that is responding to a player that is going to their left. This is the reaction time associated with someone that's going to the right. Okay, so I don't know, like let's say that's 4 centimeters and 4 centimeters. If someone gets faked, let's say they're going to the left, and then they actually go to the right, what this shows is that if they were going to the left, and then they got faked out, and there was no such thing as a psychological refractory period, if we already know the reaction time is this amount of distance, then once they realized they were getting faked out, it would be the same reaction time. But what they've noticed is that the reaction time is much more. And that's because once they get faked, the person has to sort of like go follow through with that motor program a little bit. And then they can sort of reevaluate and put out the new motor program to like follow the offensive player and defend them. So that was the psychological refractory period. And then just 2 more sort of slides. And this is internal things that influence preparation. So this is performer characteristics. So not sort of like characteristics in the environment, but characteristics that affect a person's ability to perform or prepare for the motor control of the motor skill. So the first one is the alertness of the performer. So depending on how like sort of like groggy someone is or how alert they are, it will affect their reaction time. So it'll affect their processing. So they find that when you're given a warning, it gets someone to focus in on, so the reaction time is less. If they have a long-term maintenance of alertness, so vigilance effects that came from like, you guys know, like air traffic controllers can only go for a certain amount of time. What about like truck drivers? You know how there's like an amount of time where they're allowed to drive and then they have to stop legally? That's because what they've realized in research is that the longer you're maintaining your alertness, the more you psychologically fatigue. And then therefore you get to a point where your reaction time or your processing starts to get affected. One note on the warning signal. So if you take the reaction time when you get a signal and response, if you add a warning signal, then the stimulus, then the response, it tends to decrease reaction time as long as the 4-period length, the time between warning and stimulus, is between 1 and 4 seconds, or else it's lost. One thing that we're going to see next week with like choking. Does anyone know what like choking is in sports? When performing a motor skill, it's always most important to focus on the goal or the signal than it is to focus in on your actual movements. When you overthink, like, okay, when the go signal goes, I have to do this, and thinking about internally, it screws you up. It constricts your motor system. So that will affect action preparation. And then the last little couple slides, we're just going to say, like, so what is actually occurring? So now that we know the different factors that affect action preparation, what do you guys assume is actually sort of happening? So we know that the regulatory conditions are being added, like, so your body's about your vision and everything's evaluating, you know, the regulatory conditions, modifying the motor program for that motor skill based on that situation. We have to understand as well that given the task that we want to do, we have a premotor cortex. So one thing that's occurring is that we are sort of activating our core muscles, right? And that was one thing that what they noticed in research was that when we go to perform a motor skill, the muscles that are activated first are our core muscles, and then the sort of fine control muscles. And so here we have an example of showing that. And so here we have a study where the people were asked to, or the subjects were asked to place their foot on a step. Sorry, to step, like, so place their foot on a step and step up, or place their foot with just leave it there. And what they found was that, so what the signal would do, so the signal would either be step or place. And what they found was that they measured EMG from the postural muscles, and they found that depending on which one came up, the postural muscles changed, their activations changed subconsciously. So what that means is that in that reaction time, part of it is figuring out what, based on the goal of the movement, what stability muscles you're contracting. So it just goes to show that we have a part of the brain that's processing the postural muscles. And we know now through like motor control research as well as neuroscience research that that is the premotor area. We know that in that processing time, we can estimate based on vision what people are looking at. They typically are focusing in on the regulatory conditions, right? So based on all the skills that we talked about in the beginning of the lecture, we talked about how vision is going to be used to look at the objects, determine distance, monitor movement. All of that's going to be happening in the action preparation. So all of that's going to be sort of processed together. One thing that research has shown is that we must be processing sort of like a series. We prepare sequences of movements in advance, because what they would do is they looked at the piano. I think I've talked about this before, but they look at pianists And depending on the notes that are coming up, the pianist will subconsciously alter their hand position to accommodate for notes that are coming up. And so if that happens subconsciously, the pianist must be evaluating, all right, so parts of the brain, the motor skill must be evaluating what's coming up and alter the motor skill or the hand positioning based on the notes that are going to be coming up in the sheet of music. So it just goes to show that in part of that processing, that reaction time, right? So what's happening in real time, there must be a processing of what's going to be happening in the future, and that's going to be taken into account when we're performing the motor skill. And then the last thing that they sort of noticed is that does anyone play, like, so anyone who watches basketball, what do players typically do when they are about to shoot a free throw? Or golfers right before they're going to swing the golf club? Typically, in motor skills, people have this like sort of pre-performance rituals. Can you guys think of anything? Like baseball players, before they're going to hit the baseball, they practice swinging. Before you perform a motor skill, you typically, a lot of times, it's common to see people like performing like pre-situational rituals. So what's that doing? Any guesses? Yeah, so it's the routine. So, but what about it is the routine? So it could be, I mean, it could be allowing them to focus. It could be sort of hyping them up. But what they found in some of the research was that it's priming. It is they're priming the rhythm. When you first start off cold, your coordination's a little bit off. If you practice a little bit, you get your rhythm down. It's the rhythm that the people need to practice. Cool. Now, was any of that difficult to understand for the lecture? I skipped over some of the videos, but the videos are important. If you want to look back and sort of just like watch them as you're going through the lecture again. Any questions, guys? Awesome. Okay. We are, oh, I should save it. Don't save it. We are done the lecture for today. So there's no lecture next week because it is reading week, which is awesome. And if there's any questions, please email me. I'm going to ask the TAs about the whole idea with coming up with like an example for the lab. And have a great week. Stay safe. Everything's opening up again, so yay. Okay, awesome. Bye, everyone. Bye. Bye.